So what I want to talk about is a new system that we're in the process of developing at Penn State for crediting the nitrogen availability from cover crops and soil organic matter. This is still very much in the research phase, but we've made a lot of progress, and now we're kind of fine-tuning it. I want to say up front, nitrogen management is involved in a lot of regulatory things, and so what I'm going to present here isn't changing any of the regulations in Pennsylvania, and it's not, at this point, not intended to supersede any of our nutrient management regulations and things like that. So I just want to put a disclaimer out there because I know it's a topic that can get people excited. So this is just research at this point. Maybe if as it develops and we validate it and it's seems to be working solidly, maybe it'll become an option for nutrient management planning in Pennsylvania, and maybe other states will take a look at adopting it here. But right now, I want to give it, present this as a research update on what we've been working on. Now, you all probably know that nitrogen fertilizer, there can be a lot of losses, right? It's a complex nitrogen cycle. There's leaching, denitrification, volatilization, lots of lost pathways. And so typically, our nitrogen fertilizer is only about 50% efficient in terms of recovery by the crop. And that's an issue for the environment, for water quality, for air quality that we need to deal with. And one of the tools that farmers are really getting behind is cover cropping. And it's great to be working in a region where this practice is being embraced by the farmers, being embraced by consultants like you all. And there's a lot of innovation around this practice. And it's an important nutrient management strategy for reducing leaching losses over the winter, being able to recycle that back into the soil and retain it in the cropping system. So we're lucky, as I mentioned, to be in a region where cover cropping is widely practiced. This is a survey from the National Agricultural Statistics, where we analyzed and looked at the percent of annual cropland that's getting cover cropped. And we're in a region here that's dark blue, which is the highest cover cropping rate in the nation in our region. So that's a real testament to the progressive nature of our farmers and our industry here. So one of the challenges, though, now that we've got all this cover cropping, is that our nitrogen fertilizer recommendation systems have not evolved to include the changes that cover cropping creates in the nitrogen cycle. And what I want to show you here is a little diagram that shows how Pennsylvania's nitrogen fertilizer recommendation system was developed. So this is a graph that shows 58 different trials where we had nitrogen response curves and looked at the economic optimum nitrogen rate. So that's the y-axis here is the economic optimum nitrogen rate. And then we sorted each trial in terms of their yield potential from low to high. And you can see that there's a lot of variability. There might be a slight upward trend. But to be conservative, in terms of conservative and protecting yield, the way we set our recommendation system is to bin out our yield groups into 4 different categories here and then set a nitrogen fertilizer rate that basically caps that and is at the top of the range, so that 95 to 99% of the time we've got enough or more than enough nitrogen. Now, where you see a gap between the fertilizer recommendation and the actual economic optimum nitrogen rate, that's kind of an error in our system, where we're recommending more nitrogen than that crop actually needed from an economic perspective. And there could be a lot of reasons why we have that scenario. Could be that maybe these are sites that had higher soil organic matter or more nitrogen mineralization. So we don't really take that into account right now in our current recommendation system. But as farmers use cover crops, as they build soil organic matter through no-till practices or through manure additions, we're building up a pool of mineralizable nitrogen that could potentially reduce our fertilizer rates. So currently in Pennsylvania and probably in other states that you all work in, our current adaptive nitrogen management tools have not necessarily been developed with cover cropping in mind. So for example, in Pennsylvania, we have nitrogen credits for alfalfa and red clover hay, but not necessarily annual cover crops. We have nitrogen credits for residual manure history, which might take into account some soil organic matter, building up soil organic matter through manure usage. In terms of cover cropping, if you put fall manure out, our agronomy guide has an increased availability factor of that fall manure if you're using a cover crop, so that is one way that cover crops are built in. We've got the pre-side dress soil nitrate test that a lot of people are using, and the idea with this is that if you take a soil sample in the early phase, early summer or so, when the corn's 12 to 18 inches tall, that kind of gives you an idea of the trajectory of nitrogen mineralization. So this chart here shows nitrogen, soil nitrate levels as they build up during the growing season, and eventually they get drawn down by the corn, but there's still mineralization going on. And so by taking a soil test here in the early summer, we kind of predict what the trajectory of that nitrogen mineralization might be. But the PSNT test, it was calibrated not in systems that included cover crops. It was not calibrated in systems that were under long-term no-till. And so, the nitrogen mineralization dynamics of cover crops are quite different. We might have a scenario where the legume, a pure legume like this pea here, mineralizes a lot of nitrogen early on, and if you measured that with the PSNT test, you'd say, wow, I've got a lot of nitrogen, but that mineralization might peter out pretty quickly. Same scenario with a cereal cover crop like triticale. You might have somewhat low mineralization early on, but maybe that mineralization is going to keep going further into the growing season. So we've got a changed dynamics, temporal dynamics of nitrogen mineralization that the PSNT test may not account for. So this is all to say that things change when we're cover cropping, and we need new tools to be able to account and adapt to changing dynamics of nitrogen mineralization with cover crops. So we are developing this system in Pennsylvania, and we're kind of doing research on, and I want to explain kind of the basis for the system that we're developing. The system that we're developing, the goal is to predict nitrogen mineralization from soil organic matter and cover crops. And the way we're doing this is by trying to predict the yield that could be achieved based on only mineralization of cover crops and soil organic matter alone. So that's what this brown bar here represents. Now then you know what your typical yield goal might be for your site, given management factors, climatic factors, soil factors. You've got a yield goal in mind. What we're working on is predicting what this unfertilized yield is and comparing that to your yield goal, and then you've got a yield gap here that you need to meet, and that's the yield gap that you need to meet with your nitrogen fertilizer requirement. So we can do things in terms of cover cropping and building soil organic matter that might build up the yield that we can achieve without fertilizer, and then that difference between our unfertilized yield and our yield goal is what we fertilize for. So to understand what that yield without fertilizer might be, we have to understand a little bit about the nitrogen mineralization process in order to be able to predict that based on changes in cover crop residue or levels of soil organic matter. So I want to talk a little bit about the theory and the process behind nitrogen mineralization. So here we've got on the left a decomposing residue. This might be cover crop residue. It might be native soil organic matter levels. And microbes are the organisms that are doing the decomposition process. And during that decomposition process, what the microbes are really after is the carbon. By breaking down that carbon, they get energy to build their biomass and produce all their cellular processes that they need to do. Now, some of this carbon they decompose from the residues gets built into their biomass, and the rest of it gets respired into the atmosphere. So as they generate energy to fuel their processes, the energy generated, the byproduct of that is carbon dioxide that goes into the atmosphere. And anywhere from, say, 25 to 50% of that carbon they decompose might go into the atmosphere. And that's one of the things that varies maybe depending on soil texture. So when we have clayey soil textures, typically more of the carbon goes into the microbial biomass and less goes into the atmosphere, versus sandy textures, more goes into the atmosphere and less goes to the microbial biomass. So what we call that percent that goes to the microbial biomass the efficiency, the carbon use efficiency of the microbes. Now, as this carbon decomposes in the residues, nitrogen is also decomposing based on the C to N ratio. So they decompose in synchrony with each other. So if you have 10 parts of carbon decomposing here and 1 part of nitrogen, they're going to decompose together. And what the microbes use is based on how much carbon they build into their biomass, they're going to use a certain amount of nitrogen from this decomposing material. And the nitrogen that they don't use is what gets mineralized into the soil as an available form in the ammonium form that crops can use. So this is a process where things can change how nitrogen mineralization happens. If you have a lower C to N or a higher C to N ratio, so less nitrogen here, you're going to get less excess nitrogen mineralized. It can also go the opposite way, where if you have too much carbon and not enough nitrogen, this arrow might go backwards, and we call that immobilization. Microbes will tie up that nitrogen. The carbon use efficiency can change based on soil texture. You might have more or less residues here, that creates a different size of residue that's actually decomposing. So there's a lot of factors, and that's why it's been challenging historically to account for this, because it's a complex process. It's a biological process. So luckily, we can actually mathematically create an equation that represents this process. And so we have things in this equation. This E here is the efficiency of the carbon use. We have the C to N ratio of the residues here. We have the C to N ratio of the microbes here. We have the total N content of the residues that are decomposing. And this K value just represents the rate or the speed that it decomposes. So this is an equation that we could actually use to pencil out and predict the amount of nitrogen that mineralizes from cover crop residues. So that's actually what we've done is we've taken that equation and we've developed a system of equations that you can pencil out based on some relatively simple measurements from the cropping system. So this equation, this set of equations here, we have E here for the microbial carbon use efficiency. That's based on your percent clay and your percent sand for a site. So you would measure this with just a soil texture analysis that you could get from a soil testing lab. So that allows us to predict the microbial efficiency, the percent of carbon that the microbes are going to put into their biomass versus respire. We have a credit for the soil organic matter content, so just percent SOM from a soil test that you do. We have the N content of the cover crop residue, so above ground biomass of the cover crop residue. I'll tell you how we're measuring that in a second. We've got the C to N ratio. And then we have, so that gives us a credit from soil organic matter, a credit from cover crops. We add those together, and there is a quadratic adjustment that we make to predict the unfertilized yield. So the question is, these equations, how good are they at predicting the unfertilized yield? And so we calibrated these. This number 154, this number 0.52, they didn't come out of thin air. I didn't wave my hands and make them up. We had a data set of lots of different sites, about 100 different sites where we grew corn without any fertilizer. We measured soil organic matter, we measured cover crop nitrogen, we measured cover crop C to N, we measured soil texture, and we got a pretty good relationship between the actual unfertilized yield and what we predicted the unfertilized yield. So that's the relationship there. So we're showing that we can do a pretty good job at predicting what you can yield without fertilizer based on these simple agronomic measures of the soils and the cover crops. And then we can use that to try and predict what the fertilizer requirement is. Question, Jonathan?
Your carbon to nitrogen ratio on soil microbes, is that as variable as it is in some of your above ground biomass or not?
So the question was the carbon to nitrogen ratio on soil microbes, is that as variable as we might see on the cover crops? And the answer is no. Actually, it's very static. It's very fixed. Microbes have a very fixed ratio of C to N. It's about, their C to N ratio is about 10. So that's very, very very consistent. So it's not like cover crops where if you kill it young versus kill it mature, the seed-end ratio goes from 12 to 40 or something like that. Microbes are very consistent. So actually in our equation here, that 10 is the microbial biomass, and that's something that's pretty well known and pretty constant, so we can just assume that value and fix it in the equations. So when we use these equations to predict the unfertilized corn yield here, it's a very flexible set of equations because it's based on the biological processes that occur, and they're very flexible. So we can put information in about a rye cover crop that might have a high C to N ratio and potentially immobilized nitrogen, and that would drive our unfertilized corn yield down, versus no cover crop versus a legume cover crop where that legume might have lots of nitrogen and a low C to N ratio. It's going to drive our unfertilized yield up. So these equations will capture those differences and change this yield gap and change the amount of fertilizer that we need to achieve our yield goal. They're flexible, so it also will account for differences in soil organic matter content. So from a low soil organic matter to a medium to a high soil organic matter, it's going to change what the predicted fertilizer requirement is. Soil texture is involved in it. So clay soils tend to mineralize less nitrogen than sandy soils, and so a soil texture gradient is going to change what the unfertilized yield prediction is and change our fertilizer requirement in this system. So we've got a yield gap here that we use to determine the nitrogen fertilizer. And how do we actually use that yield gap to determine the fertilizer requirement? Well, theoretically, if you look at the physiological requirement of corn to produce the mass in a bushel of grain, the crop needs to take up 1.2 pounds of nitrogen to produce that bushel of grain. So if we've got a yield gap here of 50 bushels, then the plant needs to take up 50 times 1.2 pounds of nitrogen to produce that. But we also know that the recovery of nitrogen fertilizer is rarely 100% because we have loss pathways and whatnot. So the question would be, what is that nitrogen fertilizer efficiency under this system? So we could take the yield gap times the 1.2 pounds of N required and then divide by some efficiency factor here, and that gives us our nitrogen fertilizer requirement. So what we're doing now in the research phase of this is trying to hone in on what is this efficiency factor here. That's a little bit of an unknown here. We've done a lot of research to calibrate the equations to predict what this unfertilized yield is, and the next phase that we're looking at is what should this efficiency factor be. So some of the experiments I'm going to show you here in a second, we've penciled things out based on different levels of fertilizer efficiency. Now, so that's the background on the set of equations we're using. Any questions on that? Feel free to, if you need me to stop and explain anything a little more. I think I've got enough time in my slide set here that we can accommodate some questions. Yes?
So before the gap, are you assuming that's 100% available?
Before the gap.
Like the bottom of the bar, like what's from that rye cover crop?
Yeah, so the what our equations predict would be the yield. And so it doesn't necessarily mean that the nitrogen mineralized is used 100% efficiently, but what we're saying is whatever that efficiency is, it's going to create a yield of this. So our y-axis here is the corn yield. Yep. Okay, so what I also want to talk about is how we've been testing this to develop a variable rate nitrogen prescription that represents variability that we see within crop fields and cover crop growth, soil texture, soil organic matter levels. So cover crop growth in a field, I'm sure you all have seen variations in cover crop growth within a field. This is one of the fields that we were working in, and you can see up on the edge here he's standing and the cover crops only come up to about his ankle. And he gets down in the low spot of this field, and now it's coming up to his mid-thigh there. And we can also look at satellite imagery of this same field, and you see variations. This is satellite imagery from the day we were out in the field, and you see the dark green area. That's where he is down here in the middle of the field. The yellow area here is where he is up on the edge of the field. So there can be a lot of variation in cover crops. So how do you measure and account for this variation? Well, one of the tools we're looking at is using green seeker sensors, a handheld green seeker sensor, or you could do it on a spray boom mounted green seeker sensor, and using that NDVI value to predict the nitrogen in the cover crop biomass. And so one of the big advances that we've had that makes this system a little bit more practical is using this sensor to measure the cover crop, above ground nitrogen in the cover crop biomass. So now instead of having to clip a quadrat and weigh that biomass, dry it, and whatnot, you can just walk the sensor over the field. And so we've calibrated that based on hundreds of cover crop plots where we walked the sensor over the plot, but also clipped the biomass and dried it and weighed it and did a formal lab analysis. And we're getting a pretty good relationship between the NDVI value and the biomass nitrogen of the cover crop. And so we're using that NDVI value to predict the nitrogen content. And so we can do that mounting a sensor on a spray boom and actually data logging it with GPS coordinates as well. Measuring soil texture variations in a field. There's a lot of fields that have variations in soil texture, and we're using Varus sensors or like electromagnet induction sensors to measure variations in soil texture. So electrical conductivity, these are EC maps, show you variations in soil texture. So we can use this to create different zones of the field where we pull soil samples and measure soil texture and soil organic matter separately in different parts of the field. So what I want to show you here is just an example of how we're doing this in production scale fields, creating variable rate nitrogen prescriptions, and then putting those out with production scale equipment and measuring grain yields following those treatments. So the first thing we do is start by mapping soil electrical conductivity and cover crop NDVI values. This is a little buggy we use for research experiments, but typically if you were doing this in a production scale setting, you'd probably already have an EC map that had been done previously, and those EC maps are pretty stable because they're measuring an inherent property of the soil texture. And then what I'd like to see people do is mount these green seeker sensors on their spray booms when they're spraying out the cover crop and get that coverage map from that spray pass, not necessarily make a separate operation with a little buggy like this. This is something we take around for our research projects so that we can pop in and don't necessarily have to coordinate with the farmer and get the sensors on their equipment. It makes our life a little simpler to just have our own little setup here. This is an example of a farm in Chambersburg. Leslie Bowman was our cooperator here. Just the soil EC map from his field. This is maybe 30 acres or so of one of his fields that we mapped. So you see there's variation. We kind of bin these out into 3 EC zones, and we soil sample each of these zones separately. We've got a Wintex probe on our buggy here, and we can drive to different zones and get a composite soil sample by zone, and we measure soil texture and soil organic matter to input into the equations. This is an example of the cover crop NDVI map from that particular field, and the pounds N in the cover crop biomass that we measure. So it went from a low of 15 pounds of N to a high of 135 pounds of N. So some real variations in this field. This is just a picture of what that field looks like. You can see the variation in greenness here in this wheat cover crop. And so there's definitely something going on with availability of residual nitrogen in different parts of that field. Question, Mark?
Yeah, on your EC map, what was the scale of your differences from your zones?
So I don't have the raw EC handy here on the slides, and that is also it's kind of a sliding scale. One of the things in this particular field, when we soil sampled by different zones here, we actually pulled multiple sampling points from the zones and looked at statistical differences. And even though we saw variations in EC here, we actually didn't see variations in our soil texture or our soil organic matter in this particular field. Some of the fields we did see statistical differences, some of the fields we didn't. So In the cases where we didn't see a statistical difference, we just went ahead and used the field average. Yep. But so in this case, this farm, we used the field average for the soil organic matter and soil texture, but we used different inputs of cover crop nitrogen by the different zones here. So another way that I think this might evolve into the future is instead of using the green seeker sensor to map the cover crops, we might use satellite imagery. So this is satellite imagery from the Encirca platform of this same field on the, close to when we mapped it, and you can see similarities. So this lighter area here is lower NDVI. That little patch is this little patch here. Some of the darker areas here, that patch is this patch here. A dark patch there, dark patch there, dark patch here, dark patch here. So we're seeing very similar patterns, and I think our satellite imagery is actually going to give us higher resolution than our green seeker sensors, where we're making swaths on maybe 30-foot passes here. If you had maybe 8 or 12 of these green seeker sensors on a spray boom, you might get higher resolution. But the way we're doing it here, there's a lot of interpolation that goes on in between each of our swaths that the satellite imagery kind of solves that. So that might be a way that in the future we could, and then that also saves you the hassle of needing the NDVI sensors, and you could really scale this up as a consultant using satellite imagery for fields. So I think that's something I'd like to see us work on in the future. So for this variable rate prescriptions, we also look at corn yield potential by zone, and that's going to kind of set our demand side in terms of corn yield, our demand side, the nitrogen requirement. As that crop produces more grain, it's going to need more nitrogen. So we're looking at both the demand side and also the supply side from the soil organic matter and cover crop residues. So ultimately what we do is we take all those data layers, we take the cover crop nitrogen, we take our soil zones, we take our yield zones, we intersect those in GIS and create different zones for a fertilizer prescription. And this gives you an example of our side dress prescription map in this field. The farmer put on about 52 pounds of nitrogen at planting, and so we're looking at, we credit that 52 pounds of N and then say, what do we need additionally to meet our corn yield goal, also crediting the nitrogen supply from cover crops and soil organic matter. And that's what a prescription map would look like. Now, I want to just give you a little rundown on the 4 sites that I'm going to present here in terms of basic parameters of their soils and cover crops. So we had 4 sites, and I'll go through them one by one here. Warriors Mark, which is in central Pennsylvania, near the Penn State campus and State College. Our yield goal ranged from 110 to 270 bushels per acre. Our cover crop nitrogen ranged from 15 to 45 pounds N per acre. The cover crop C to N ratio was pretty consistent around 18. This cover crop was a cereal rye cover crop. All of our examples here were cereal cover crops, either rye or Chambersburg. We used wheat. Soil organic matter, 2.2%. Sand ranged from 12 to 21%. So this was a site where the EC maps showed variation in soil texture. And then the clay percentage, 34%. Danville, which is in central Pennsylvania, 119 to 210 bushel per acre yield variation. Cover crop, 15 to 45 pounds N. C to N ratio, pretty high, around 29. Soil organic matter, 2.6%. For Pennsylvania, 32% sand is relatively high, and so this actually drove our microbial carbon use efficiency down and our nitrogen mineralization up. And so we were actually predicting that this 29, a C-to-N ratio of 29 would still mineralize nitrogen from this field. In Chambersburg, yield varied from 125 to 350 bushel per acre. Cover crop N, very wide variation from 25 to 135 pounds of N per acre. C to N ratio varied from 10 to 27. Soil organic matter, 2.4%. Sand, 17%. So relatively low sand and relatively high clay at this site. And what that actually did is drove some of this high CN ratio material to immobilize, versus the low C/N ratio material was going to mineralize in our equations. So this is a scenario that I've actually seen this other sites we've looked at, where part of the field you're going to have a mineralizing cover crop, part of the field you're going to have an immobilizing cover crop. And I think that speaks to the importance of doing kind of zone management and variable rate prescriptions so that we actually credit those different parts of the field differently that have variations in soil texture or cover crop nitrogen and C/N ratio. At the Rock Springs site, which is our research station, 50 to 210 bushel yield range based on historic yield maps. Cover crop N ranging from 25 to 65 pounds of N. Cover crop C/N ratio was pretty consistent around 24. Soil organic matter based on the zone 2.5 to 3.5%. Relatively low sand content, 17%, and we had some zones that had clay up to 49%. So this actually 24, C/N ratio of 24 here in our equations was predicting to be a pretty heavily immobilizing cover crop. And so that's going to prompt us to put more nitrogen on than we would typically expect without the cover crop. So this is the 4 sites here that I just showed you. Remember I said we're trying to hone in on what the efficiency should be in our fertilizer calculation. We predict that yield gap. We multiply that yield gap times 1.2, and then we divide by the fertilizer efficiency. And we don't know what that fertilizer efficiency value should be in using systems like this. So we tested a prescription based on 100% efficiency recovery, 75% recovery, 50% recovery. So that's what these 100, 75, 50% mean. And then we compared it to the agronomy guide. So our typical agronomy guide calculations, which we use for nutrient management plans, it calculates nitrogen based on 1 pound of N per bushel of expected yield, minus credits for manure history, and minus credits for fall manure applications. So some of our sites had a fall manure application with a cover crop. So when we look at this, typically we'll see our 100 to 75 to 50% efficiencies go up. And then what's interesting is sometimes, like our 50% efficiency is calling for more than the agronomy guide recommendation. Sometimes it's calling for less than the agronomy guide recommendation. Going into this, I kind of thought, you know what, our agronomy guide, very conservative. It's always going to protect for yield. But actually what we're seeing is when you add a cover crop, especially like a very mature cover crop, sometimes these calculations are saying you need more nitrogen than our typical recommendations would be. A couple of things to point out here. This site here had a pretty high sand content, and that in the equations is going to predict more nitrogen mineralization and a lower fertilizer requirement. The Chambersburg site here had a high clay content, and so that's going to suggest less mineralization and create a higher nitrogen credit. The agronomy guide here, this value got pushed down quite a bit because of fall manure credits and residual manure history credits. And so that pushed that value down. The other thing is our 50% efficiency here. Typically, you'd see this bar be much higher there. You'd see that bar, if it followed this kind of stair-step pattern, the 50% efficiency should have really been up here. But we actually hit the limits of what the sprayer could do based on its nozzles, and we actually, we kind of maxed out that rate there. So this rate isn't actually 50% efficiency; it's more like kind of 68%. So, okay. So throughout the year, throughout the growing season, what we did is we measured some intermediate variables during the growing season to look at nitrogen availability. We measured %N in the corn ear leaves, and that's what these data are here. Our sufficiency range is from 2.75% to 3.5%, and only a couple of these treatments got into that sufficiency range. So Warrior's Mark got up there for most of the treatments. Danville, the agronomy guide treatment got up there. Chambersburg, the 50% efficiency, the mean value there, which is the X, got up there. Rock Springs, our 50% efficiency is kind of right at the bottom level there, but the agronomy guide got up there. So we're starting to see some indications that like 100% efficiency and our 75% efficiency levels probably not cutting it. We may need to use 50% in our equations. We looked at cornstalk nitrate results at black layer, and our optimum range is in the 700 to 2,000 parts per million. The actual research-based critical level, so the critical level at which yields really start to drop off, is actually only 250 parts per million, but we kind of create a buffer in terms of our extension recommendations to create that buffer a little higher. So we saw that except for the Warriors Mark site, all of our treatments averaged below this critical level. And so we may need even more nitrogen than like the 50% recovery level. One of the things we experienced in Pennsylvania this spring was extremely wet weather. One thing to note is the Warriors Mark site was the only site where the farmer included a nitrification inhibitor in the UAN. And so, that probably protected against some denitrification losses that maybe we saw in these other sites. Most of the sites put on about 50 to 70 pounds of N as starter, either through the burn down or with the planter. So, that's something I think, we should all be thinking about with increasing wet weather in the springtime. So finally, the yield results. What we saw in terms of yield here is that typically our 50% efficiency was equivalent to or sometimes better than the agronomy guide. So Warriors Mark, 50% and agronomy guide recommendations came out to be the same yield-wise. Danville, statistically not different between 50% and agronomy guide. Numerically, there is quite a difference in terms of the averages there, and so, this would be a site where maybe, a nitrification inhibitor might have helped save some nitrogen, and but also our 50% efficiency there may not have been quite enough. At the Chambersburg site, where the 50% efficiency called for more nitrogen than the agronomy guide, we saw a statistical difference between the gray bar here, which is 50% efficiency, and the yellow bars here, which is the agronomy guide. We saw an increase in yield there, and so the equations led us to that higher nitrogen rate based on having a potentially immobilizing cover crop, based on having a higher clay content, led us to that higher rate than the agronomy guide. And so I think sometimes, these tools might help us identify sites that, because of cover crop immobilization, need more fertility. So just to conclude here, and hopefully we'll have a little time for questions, I think this tool holds promise. We're still working out some of the bugs, but it's based on biological first principles of nitrogen mineralization. And using those first principles allows us to be very flexible in what we can accommodate. We can accommodate changes in soil organic matter levels, changes in cover crop nitrogen, changes in cover crop C to N ratio, changes in soil texture. All of those are built into this system in terms of being able to make adjustments. We can use a variety of sensors and imagery that can extend these concepts into variable rate nitrogen prescriptions that account for differences in zones within fields. So far, our data suggests that we need to use about a 50% fertilizer efficiency in these calculations to be able to maintain our yield levels. In a wet year like we had, nitrification inhibitors at the one site seemed to boost our stock nitrate levels, and that's something that I think we should be thinking about to help prevent nitrogen losses. Rates with this tool were sometimes higher than our agronomy guide recommendations, and this is where I don't want people to get too excited, because I hear a lot of people that say I can't get my yields when I'm following my nutrient management plan, and so maybe we'll get this worked out and eventually create this as an option that you can have in a nutrient management plan, but it's not there yet. We're still in research phase. And we also need to test this tool in some really high organic matter soils. So the sites we had here were kind of moderate soil organic matter levels. We had cereal rye cover crops that were potentially immobilizing some nitrogen. It'd be great to test this on some high soil organic matter sites and sites with big, luscious legume cover crops. See what we can do in terms of, on those sites, predicting reduced nitrogen requirements compared to our agronomy guide values. So I'm looking for sites like that in the future. And then, of course, we're going to keep collecting data and try and validate what that efficiency level is. Should it be 50%? Should it be 60%? Should it be 40%? We're going to try and dial in on that because that's a big factor that changes what the fertilizer requirement is. It can change it quite a bit. So I want to thank our farmer collaborators from this past year, research technicians and farm staff, grad students that have worked on this project, folks at Granular, Kelly Urbick, kind of opened up their platform for us to get satellite imagery and look at their tools, so I'm really appreciative for that. Some consultants that we work with in Pennsylvania and New York on this. And this project was funded by Northeast SARE through a on-farm partnership grant. So, Mark, how am I doing on time?
You've got 9 minutes for questions.
Okay, 9 minutes for questions. One thing I want to mention is I have some handouts up here. If this really interests you and you want to see the equations, there's a kind of a worksheet that shows you the equations and allows you to put numbers in and pencil things out. There's also for our green seeker calibration, there's a fact sheet on that has the numbers so you can look up your NDVI value and predict the cover crop N. So that's up there. If there aren't enough handouts to go around, just email me and I'll shoot you a PDF of those documents.
Are they online on your extension?
They're not online yet. The Green Seeker one, we're in the process of getting that posted to our as an extension agronomy fact sheet. Yep. Okay, Jonathan.
Your 50% for nitrogen, is there, when you're using some of your other tools for measuring losses and things, can we get that better and utilize this in conjunction, or what are your feelings on that going forward?
Yeah, so I think we can get it forward. I think we can potentially move it forward through, nitrification inhibitors, and these were all split applications too of side dressing, which should help things. The other thing about that percent efficiency is in these equations, that's almost more of a fudge factor than it is like a true fertilizer recovery. We're not actually using like N15 labeled fertilizers. We don't have unfertilized checks where we can do traditional nitrogen use efficiency calculations. So I would say don't necessarily look at those numbers as a true fertilizer recovery. Look at it more as like a fudge factor. And some of it also has to do with kind of the quadratic yield response and kind of diminishing returns to nitrogen. Some of that just nature of yield response is kind of what pushes that efficiency down a little bit too. But, thinking about it in the long term and in a systems perspective, yeah, we're probably going to have some residual nitrogen left over. That's just going to be a fact of life. And I think, trying to cover crop as consistently as we can, we're going to catch that nitrogen. We can recycle it back. But the big question is when we recycle it back, how much are we actually recycling in an available form versus how much is getting immobilized and being built into long-term soil organic matter? And that varies a lot based on your management of that cover crop, when you kill it, what the species composition is. And so I think cover cropping in combination with equations that allow you to capture that and be flexible with that, I think will be kind of create a sustainable system where we can account for all of that and trap the excess nitrogen that we do have, recycle it, and just kind of keep perpetuating that system, that recycling system with the cover crops. Yep. Other questions? Yes?
Were you corn versus corn following corn, or were you corn following soybean?
Yeah, so it actually varied depending on the site. We had corn following wheat. We had corn grain following corn silage. We had corn following soybeans. So there was a lot of variability. One of the things on our corn following soybeans site, we actually decided on our agronomy guide calculations, we decided not to credit the soybean credit. It was 62 bushel soybean crop. So our agronomy guide would say take 62 pounds of nitrogen off. But we had this tall cover crop here, tall rye cover crop that was headed out, and I kind of think a lot of that soybean credit is from stored nitrogen in the soil profile over the wintertime being still available, and I knew that rye cover crop had basically sucked that down to zero, and so I kind of made a professional judgment decision not to credit that in the agronomy guide rate. And I'm kind of glad I did, because that agronomy guide rate still, I think we needed that full rate under that scenario. So
That was going to be my follow-up question. We're now required to use 1 pound per bushel. When we're getting 80 bushel beans, I really don't see we're getting 80 pounds of nitrogen for next crop.
yeah. And I think that's another scenario where, when we've calibrated our nitrogen recommendations, we have not historically calibrated them with a cover crop. And some research that I want to do is, does a big cover crop like that kind of invalidate the soybean residual credit? We're going to try and do some research to look at that. But I also want to say it's regulatory stuff, and we've got nutrient management plans in Pennsylvania, and you've got to take that soybean yield credit. So for now, nothing changes, but I think, theoretically, I think there could be a difference, and that's something, at least in Pennsylvania, I want to take a look at and see if we can make some allowances there based on new data with our cover cropping systems. Yep. Yes?
Did you say they were planted green, or was everything burned off first?
Some of the sites did plant green. So Chambersburg actually planted green, and Danville planted green, and then burned off, a day or two after planting. So I do see that kind of rising in popularity. And by planting green, like Chambersburg, that wheat had not headed out yet or anything like that, but it was still very dense and lush. So I think, some people think planting green is you got to have a huge rye cover crop that's already headed out and create this massive mulch layer. I see a lot of farmers that treat planting green as just planting into whatever's there and then spray it out, and it gets called planting green. So I think there's some variations in terminology and practice that we're not always on the same page about what planting green means. Yes, Bob?
Very interesting talk. You made a comment about the IR photography from the satellite.
Yeah.
You've got a very good program to get it work for the variable yield application of the fertilizer. How hard is it going to get the satellite data timely to do this? Or is it something you can get very easily?
So the satellite imagery through, I've used both the granular and also climate field view, and I want to be fair to everyone and not favor one over another. They're both good services. They come in a very timely manner, almost not the same day, but within a day or two later. The challenge I see is cloudy weather. I get a lot of gaps, week-long to 10-day gaps in terms of cloudy weather, and even just like, scattered clouds will cast a shadow that can kind of confound things.
That brings me to the second thing. If you can fly drones with the proper equipment on it, can you get it? Can you make it work that way too?
Yeah, we've looked at drones, and drone imagery is pretty similar to satellite and pretty similar to what we get with the ground-mounted sensors. Drones, I think, have their own disadvantages. So I've worked with drone guys, and they're like, oh man, it's partly cloudy today, we can't do it. Or, so they want either full sun or they want full cloud, and then, and at least the guys I'm working with, they're researchers that are like, okay, we got to file our flight plan, and well, this guy's off today, and so, like, at the end of the day, it never gets done. It never gets done. Whereas you got those eyes in the sky that are running, 24/7 and brought to your smartphone or your desktop. So,
With that, I'd like to thank our speaker.
All right, thanks everyone.